Hello, today in this lecture we discuss Nowhwre dense sets. So this is the unit second of your course topology. So let's first define Nowhwre dense sets. So, Nowhwre dense sets. Nowhwre dense sets. So let given a metric space xt, let xt be a metric space, and this A is a subset of X. We say that A is Nowhwre dense if interior of a closure is the empty set. Okay, that's the definition. So a closure does not contain, in other words, a closure does not contain any open sphere. In other words, a closure does not contain any open sphere. Okay. Examples. So let's take the real line. Consider a real line R. Consider the real line R. Okay, this is R. Then following subsets of R are Nowhwre dense. Nowhwre dense. First one is Z, a set of positive integers. Second, any finite set. Okay, but not any countable set. Okay, because Z is countable set. It's Nowhwre dense, but Q is also a countable set, which is not Nowhwre dense. Any finite set. Okay, any finite set. So if you want to solve this, we first find a closure of Z. Okay, what's Z closure? Z closure is, by definition, Z union Z derives set of limit points. That Z union the empty set, because integers has no any limit point. Its derived set is the empty set, so it's just set. So which implies that interior of Z closure is same as interior of Z, that's equal to what? This is equal to the empty set. So which means that Z is Nowhwre dense. Now second you want to see, so let A be any finite set. Let A be any finite set. Okay. Then you can see this A closure, which is equal to A union A derived, that's equal to A union the empty set, which is equal to A. So this means interior of A closure is same as interior of A, but A is the empty set, so that means interior of A must be the empty set. A is a subset of real line. Okay. And one more example. If we have this, A is this set 1 by n. Okay, where n is greater or equal to 1. Then you can see this A closure is not same as A. So in the above examples, A closure was same as A. अगर आप इस एग्जांपल में देखना चाहोगे एक क्लोजर इसी सेट ऑफ इंटीजर्स में देखना चाहोगे वहाँ पर भी एक क्लोजर ए के बराबर है, बट हियर इन दिस एग्जांपल वी सी दैट ए क्लोजर इज नॉट इक्वल टू ए क्लोजर इज बिगर देन ए, बट स्टिल दिस ए इज Nowhwre dense. So let's see this then what's a closure? A closure is the set, it contains 0 also, 0, then 1, 1 by 2, 1 by 3, so on and so forth. But the interior, but interior of a closure you can easily verify it is the empty set. So therefore this set A, it's 1 by n, is A is Nowhwre dense. These are the examples of Nowhwre dense sets. Nowhwre dense set. So there are sets which are not Nowhwre dense, like set of rationals. So prove that, show that exercise. Show that the following subsets of the real line are not Nowhwre dense. The first one is let's take Q, the set of rationals. Second is its complement. Third, you can take any interval, whether you take semi-closed, closed, or any interval, okay? And fourth, the whole real line is also Nowhwre dense. Whole real line, it's also Nowhwre dense. Any interval is Nowhwre dense, okay? So you can easily verify these because you know that Q closure is the set of all real numbers and interior of the real is real, okay? Interior of Q is the empty set, but its closure is R. The interior of R is not empty, okay? Similarly, Q complement, the set of rationals, इसका जो closure है that's also whole real line, okay, whole real line. So which means that interior of Q complement closure is R. It's not empty set. Same is true for this set. The closure of this set is the closed interval AB, and interior of the closed interval AB is the open interval AB, which is non-empty set. So R is also Nowhwre dense. It's simple. So these are examples of sets which are Nowhwre dense and the examples of sets which are not Nowhwre dense. Now we have some important characterizations, some important these equivalent forms of Nowhwre dense sets. Let's write that in the form of following theorem. The following statements about the Nowhwre dense sets are equivalent. The following statements about the Nowhwre dense set, about the Nowhwre dense sets are equivalent. The first one is, first A is Nowhwre dense. A is Nowhwre dense. It's equivalent to a closure does not contain, a closure does not contain any non-empty open set, any non-empty open set. And third one is each non-empty open set, each non-empty open set, okay, has a non-empty open subset, has a non-empty open subset which is disjoint from a closure, disjoint from a closure, okay. And fourth one is each non-empty open set, each non-empty open set, each non-empty open set has a non-empty open subset disjoint from A, has a non-empty open subset disjoint from A, right? So fourth one is this is now fifth one, okay, this is now fifth one. Fifth one is each non-empty open set, each non-empty open set contains an open sphere, contains an open sphere, contains some open sphere disjoint from A. Okay, these statements are equivalent about Nowhwre sets. So we prove 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, then finally 5 implies 1. Prove 1 implies 2. It follows from definition, you can see it actually. 1 implies 2. Suppose A is Nowhwre. Suppose A is Nowhwre dense. Now by definition, interior of a closure is empty, okay. This is by definition. We show that a closure does not contain any non-empty open set which is disjoint from a closure. So assume on contrary that so what we have to prove, this a closure does not contain a non-empty open set. This each a closure does not contain a non-empty open set, that we have to prove. Assume on contrary that a closure contains a non-empty open set, say U, let's use non-empty and use subset of a closure. So which means that interior of U is subset of interior of a closure. But U is open, that means U, interior of U is same as U, it's subset of interior of a closure, okay, it's subset of this. But this U is non-empty set, and non-empty set is contained in the interior of a closure, which means that interior of a closure is non-empty, a contradiction. As required. So this means 1 implies 2. Now 2 implies 3. 2 implies 3, right? So we assume that a closure does not contain. Assume that a closure does not contain any non-empty open set. Okay, non-empty open set. आपको थर्ड प्रूव करना. थर्ड मीन्स you have to prove that every non-empty open set contains an open set, non-empty open set which is disjoint from a closure. So we show that each non-empty open set contains an open set, non-empty open set, exactly, non-empty open set contains a non-empty open set disjoint from a. ये आपको प्रूव करना है. So we prove that, we show that each non-empty open set contains a non-empty open set disjoint from this disjoint from a closure. So we assume again on contrary. Suppose we have to show that each non-empty open set contains an open set disjoint from a closure. Okay, so we assume that suppose this is not true, then there exists an open set such that non-empty open set such that every non-empty open set contains in that set disjoint from a closure. So assume on contrary that there exists an open set, say G, such that non-empty open set, that's an important, there exists a non-empty open set, this is very important, non-empty, exists a non-empty open set such that every non-empty open set contains in G is disjoint from a closure. Is not disjoint from, is not disjoint from a closure, right? This is by assumption. So that is if U is a non-empty open subset, G is itself open, okay, of G, then U intersection a closure is non-empty. We show that this G is a subset of a closure, okay, because our assumption is that a closure does not contain any non-empty open set, and we have to prove that this every non-empty open set contains a non-empty open set disjoint from a closure, and we have assumed on contrary that there exists a non-empty open set G such that every non-empty open set contained in G, every non-empty open set contained in G is not disjoint from a closure. That is, if U is a non-empty open subset of G, then this holds. So let's try to prove that every element of G is in a closure. Okay, every element of G is in a closure. So we prove that every element of G which is not in A is a limit point of A actually. So let X belongs to G minus A suppose. Okay, we show that कोई भी एलिमेंट जो G में है मगर A में नहीं है, हम प्रूव करेंगे वो जो एलिमेंट होगा वो किस में है, वो A डिराइव्ड में है, वो लिमिट पॉइंट है इसका. जो भी एलिमेंट G में है बट नॉट इन A, we will show that that element is in A closure. It means that every element of G is in A closure. क्योंकि G में जो भी एलिमेंट होगा या वो तो या A में होगा या A से बाहर हो सकता है. तो अगर A से बाहर है हम प्रूव करेंगे वो A डिराइव्ड में है, लिमिट पॉइंट है A का, और अगर A में है देन आपको कुछ करना ही नहीं है. तो दैट मीन्स इन अदर वर्ड्स वी आर प्रूविंग दैट एवरी एलिमेंट ऑफ G इज इन A क्लोजर. तो इसको प्रूव करने के लिए हम क्या प्रूव करें, हम प्रूव करेंगे जो भी ओपन स्फीयर होगा जिसका सेंटर X है, दैट ओपन स्फीयर मस्ट इंटरसेक्ट्स विद A अदर देन X. अदर देन X तो होगा बिकॉज X इज नॉट इन A. So let R be any positive number. R be a positive number. Okay. Then obviously this holds because as R by 2 is an open subset let R be any positive number. So we need to show that X is in a derived set. Okay. So this X is in G but not in A, so it's in G. So it is an interior point of G, so there is an open sphere. There is an open sphere with interior X and some radius positive. So positive radius such that open sphere is subset of G. Subset of G. Okay. So that open sphere is subset of G. Is okay here. Okay. So let's choose R not a positive real number such that S R not of X, okay, is subset of G. Is subset of, let's write this as R1. Okay, R1. Right, R1 and R0. This is a subset of G. This is subset of G. Okay, and let's choose. Let's define a number R which is minimum of these two, R1 and R0. So let's take this R be equal to minimum of R1 and R0. Then S or X is subset of G because it is the minimum. Okay, so then this is subset of G. Now this is a non-empty open subset of G, so by definition, so this implies this is also subset S R by 2 X is also subset of G because you are reducing the radius, half radius, which means that S R by 2 X intersection a closure is not equal to 5 because our assumption is that every non-empty open subset of G intersects with a closure. So now we choose a point which is in the intersection. Let Y be in the intersection S R by 2 X intersection a closure. So our does mean it means that distance between X and Y is less than R by 2 and Y is in a closure. So that means we have a sphere with center at R and X is in that sphere. Obviously X is in the sphere of radius of center Y and radius R by 2, such that that sphere contains Y, and that sphere also this Y, where is this Y? This Y is an A closure. Okay, this Y is an A closure. So it means that what does it mean? It means that that the sphere with center at Y and radius r by 2, वो जो sphere होगा that must intersect with A के साथ वो intersect करेगा. That's very important. Does it intersect with A, this sphere? So it means that this X, where is this X? X is not in A. X is not in A. Okay. X a point which is in G, but here this X this sphere. Now if you change this center of change करोगे, you have this sphere here. This is X, this is R by 2, and you have taken a point from this. Distance is less than R by 2, then you choose another sphere, this sphere जिसका center of Y है और radius same R by 2. This sphere, does this sphere intersects with A, and if it intersects, what is the point of intersection here? S R by 2 is a subset of A. Okay, S R by 2 of Y. Y is an A closure. Okay, Y is an A closure. So Y is an A, R is an A derived. Okay, Y is in the intersection actually. So Y is in A. Okay, if Y is in A, every open sphere with center at Y and radius R by 2, this should intersect with A actually. So this distance is less than R by 2, and Y is an enclosure. And Y is an enclosure. Does it mean that the sphere with radius R by 2 and center Y intersection A is non-empty? Does it mean that this Y is an enclosure, Y is not an A, but this X is in G. Okay, X is in G. Let's choose okay, if Y is an A, if Y is an A derived, I will see here, but so okay, if this Y is an A, then we are done, because then we have a sphere, then this sphere is then this intersection will be non-empty because Y is the common point. Y is then common point. Okay, if Y is also in A, but if Y is not in A, if y is not in A, if y is not in A, then y must be in the A derived. In that case, y is the limit point. Okay, it's, I think it's okay. So here, so this is the point actually. Let's say we have to prove this actually. So this y is in A closure. So in case y is in A, if y is in A, if y is in A, if y belongs to A, then S R by 2 y intersection A is non-empty, okay, because the y is the common point. Now if y is not in A, then y must be A derived, because as y is in A closure. So in that case, since then y is the limit point, therefore every open subfield with center at y must intersect with A. So then obviously this holds, as R by 2 y intersection A is non-empty. So let's choose the point of intersection. So let's choose x dash such that x dash is in A. So choose x dash in A such that x dash is also lies in this sphere, such that this x dash also belongs to the sphere. SR by 2 y, that is x dash lies in A and distance between x dash and y is less than R by 2. Less than R by 2. Okay, so now we have distance between x and x dash. You apply triangle inequality, it's less or equal to distance between x and y plus distance between y and x dash. So both are less than R by 2 because d of xy is less than R by 2, so it's less than R by 2 plus R by 2, that's equal to R. So which means that this x dash, the point it is in, it's where it's in SR x. X dash is also in A and x dash is also in SRX. That means x dash belongs to SRX intersection A. So clearly this x dash is not equal to x because x is not in A and this x dash is in A. So this sphere intersects with A, but this means SRX intersection A is non-empty, which means that SR1x, where R1 is any positive number, intersection A is also not equal to 5. Why? Because R is the minimum of that R1 and R0. So that means any sphere with center at x intersects with A, which means that this x is in A derived. So any point which is an open set but not in A, it is in A derived. So that means thus G is subset of A closure, a contradiction, because G is an open set, non-empty open set, and our assumption is that A closure does not contain any non-empty open set, a contradiction. So this is a second implies state. So this part was a little tedious, but other parts are trivial actually, the remaining parts. Now we have a third implies 4. So you can see this J.F. Simmons for this these equivalent statements. So next we show that third implies 4. So suppose every non-empty open set contains a non-empty open set, non-empty open set disjoint from a closure. So we need to show that every non-empty open set contains a non-empty open set disjoint from a. वो हमें prove करना है. Fourth, we show that every non-empty open set contains a non-empty open set disjoint from A. Okay, disjoint from A. So let G be a non-empty open set. G be a non-empty open set. आपको प्रूफ क्या करना है? दिस non-empty open set has a non-empty open set disjoint from A. और ये आपके पास given है. Every non-empty open set contains a non-empty open set disjoint from a closure. So then there exists a non-empty open set U contained in G such that U intersection A closure is non-empty. Okay, empty set. This means disjoint from A closure. This is given. Since A closure is bigger than A, this means U intersection A is also empty. So that means every non-empty open set contains a non-empty open set U disjoint from A. So which is fourth, जो आपको प्रूव करना था. So third implies 4, done. Now fourth implies 5. Fourth implies 5. So fourth is given. So suppose that every non-empty open set contains a non-empty open set disjoint from A. We prove that we prove that every non-empty open set contains a sphere. Disjoint from A. So let's take any non-empty. Let G be a non-empty open set. What's given here? So given is this: every non-empty open set contains a non-empty open set disjoint from A. Let G be an open set. Then by fourth means the given assumption, there exists a non-empty open set U subset of G such that U intersection A is empty. Okay, now U is non-empty, so choose a point. Let X be in U. Since U is non-empty open set, so we have point X in U. Now this X is the interior point of U, so then there exists R positive such that SRX is subset of A. Now let's see this. Name it 1. intersection of U with A is the empty set and SRX is subset of U, so that means intersection of SRX with A is also non-empty. So by one SRX intersection A is non-empty. So this SRX is subset of A is subset of G. So that means every non-empty open set contains a sphere which is disjoint from A. That's this last part 6. This 5 one. Okay. Now finally we show that 5 implies 1. 5 implies 1. So assume that every non-empty open set contains a sphere which is disjoint from A. We have to prove that A is Nowhwre dense. We show that A is Nowhwre dense. We show that A is Nowhwre dense. That is, A is Nowhwre dense means that interior of A closure is empty. So assume on contrary that this is non-empty. Assume on contrary that interior of A closure is non-empty. Now interior of any set is an open set, so that means this is a non-empty open set. Then interior of A closure is a non-empty open set, is a non-empty open set. Now by fifth, every non-empty open set contains a sphere. So therefore there exists or positive such that this SRX is subset of interior of A closure, and SRX intersection A is disjoint from this. So that means we have a sphere with center at X such that sphere does not intersect with A, so which means that X is not the limit point of A. X is not in A derived. So this X is not in A derived set, okay? It's not the limit point of A, so it means that if X is not in A derived, so what does it mean? X, where is this X? This X is in interior of A closure, so it is in A closure. So X is not in A derived here. X is not in A derived, and this X is this X in A. So this is 8 or positive. So for every such X, okay, for every X I can find. So there is a sphere, okay, which is contained in interior of A closure. So that means every point of the sphere is in interior of A closure, and this interior of A closure is subset of A closure. So in particular, the center of this sphere is also in A closure, but it's also not in A. X is also, because SRX intersection A is non-empty set. X is not in A, and X is not in A derived as well as in A, because the SRX this SRX contains X, okay. So X is not in A, and also this sphere, there is a sphere SRX which does not intersect with A, which means that this X is not the limit point of A. So it means that X is not in A closure because it's not in A and not in A derived. It's not in the closure. So that means x is, which means that x is not in the interior of a closure, because interior of a closure is subset of a closure. So which means that here you can see x is not here in the bigger set, so it's not in the SRX, which means that x is not in SRX, which is a contradiction. A contradiction as required. So this was some equivalent statements for Nowhwre dense sets. So one more statement that you will apply in future, which is the following: A is Nowhwre dense. A is Nowhwre dense if and only if every non-empty open set contains a sphere disjoint from E. So this statement you will use this one, okay? So in fact you will use this statement in Bayes category theorem. So this was some equivalent forms of these Nowhwre dense sets. Now next we define a first category set and a second category set. So what's the first category set? What's first category set? Okay. So that's the definition. If X is a matrix space, if X is a metric space and D is subset of X, D may be X, okay, it's any subset of X, we say D is of first category. We say D is of first category if D can be expressed as a countable union of Nowhwre dense sets. Nowhwre dense sets. If it's a countable union of Nowhwre dense sets, we say that D is Nowhwre dense. That's if D is equal to union A and N runs from one countable union, means that we can enumerate them where they are all Nowhwre dense sets, where interior of A n closure is the empty set for all n greater or equal to 1. Now if D is not of first category, then we will say that it's of second category. If D is not of first category, then we say D is of second category. Okay, so here are examples of first category. In fact, this every singleton subset of real line is of first category. Every singleton subset of the real line R is of first category. So let's take any singleton. Let X be a singleton subset of X. Okay, this R, sorry, of R. right? Then the interior of this X closure, since X is singleton set, its closure is the set itself, and interior of singleton sets finite set. So this X is itself a Nowhwre dense set, so which implies that the singleton sets are Nowhwre dense. This is Nowhwre dense. So which means that any set which is Nowhwre dense is obviously of first category, is of first category, because it's the countable union of Nowhwre dense, which it's actually the union of single set, okay, which is Nowhwre dense. So single set, it's obviously a countable collection. Now next exercise is show that every finite set is of first category, is of first category. Every finite set of R, finite subset, okay, finite subset of R is of first category, right? Solution, so let's take any finite set. Let A be any finite set. Suppose it's consisting of n elements, be a finite subset, be a finite subset of R. Then this A can be written as this countable union, singleton x1, singleton x2, singleton xn, and this is the countable union of singleton sets, and each singleton set is Nowhwre dense. So that means A is a countable union of Nowhwre dense sets, which means that A is countable union of Nowhwre dense sets, and hence A is of first category, and hence A is of first category. Okay. Next exercise, show that any countable subset of R is Nowhwre dense. Show that any countable subset of R is Nowhwre dense. Nowhwre dense. Solution, it's very simple. Let A be a countable set, any countably infinite, okay, क्योंकि finite तो हमने कर लिया ना, any countably infinite subset of R is. So let A be a countably infinite subset of R. Then A is of this form. We can enumerate the elements of it. Then A is of this form, x1, x2, because there is a bijection from A to the set of positive integers. So we can enumerate it like the set of positive integers, or we can list this as like this set, indexed by the set of positive integers. So this is our A. Now this A can be written as, this is singleton x1 union singleton x2, okay, and union so on and so forth. That's equal to union singleton xn and runs from 1 to infinity. So that, and each singleton set is Nowhwre dense, and it's a countable union of singleton sets. That means it's a countable union of Nowhwre dense sets. So which means that A is a countable union of Nowhwre dense sets, and hence is of first category, is a first. तो जो भी काउंटेबल सेट है वो Nowhwre फर्स्ट कैटेगरी है. सो इसमें एग्जांपल्स आप ले सकते हो काउंटेबल सेट की. Z है क्यों है दे आर नोवेड सेट्स. तो नेक्स्ट जो है नेक्स्ट अब आर है. व्हाट अबाउट आर इज अ फर्स्ट कैटेगरी और अब सेकंड कैटेगरी. सो दैट्स अ क्वेश्चन. तो सेकंड कैटेगरी की कोई एग्जांपल है या नहीं है? Does there exist any set which is of second category? The answer is it's given by Beer's category theory. In fact, he proved that every complete metric space is of second category. Every complete metric space is of second category. So before proving that, let's prove some more basic results. So exercise. Show that countable union of Nowhwre sets is again countable union of this first category sets is again first category set. Show that countable union of first category sets is again a first category set. First category set. तो इसमें सिर्फ एक ही रिजल्ट यूज होगा, दैट्स काउंटेबल यूनियन ऑफ काउंटेबल सेट्स इज अगेन अ काउंटेबल सेट. वो आप यूज कीजिए, यू विल गेट दिस रिजल्ट. इट्स वेरी सिंपल. काउंटेबल यूनियन ऑफ फर्स्ट कैटेगरी सेट्स इज अगेन a first category set. That's the end of this lecture.